All right, line V1, we're in learning task 4, which is going to be dealing with selection of AC motor starting equipment. And really this whole learning task is based around understanding of our AC motors, which we've talked about a little bit before, and then understanding how the different types of motors we are going to apply are going to go and start up or inrush or other things that could potentially affect other stuff on our systems. It's our job to control the lightning, therefore we have to make sure that we're doing so intelligently that we are going to go and have the right types of starting for the right types of application. All right, we've got two main ways that we can go and start up a motor, and they're going to be split into two very distinct types of categories. We'll start with splitting these things down. The first one that we have is going to be full voltage starting. Full voltage starting is also sometimes known as across the line starting. And basically, it just means that we are going to go and take a set of contactors over here, and we are going to go and directly apply them to the motor itself. So that motor is going to go and get full voltage, and it's going to go and start up. We are going to go and get maximum starting torque because we are going to go and be able to have maximum inrush to this, right? There's nothing, no restriction other than the contactor itself ahead of that. And we're going to go and have the shortest amount of acceleration time because we're dumping in all of that current at the same time. We're going to be able to go and speed this thing up. But because we do have that large amount of inrush, I mean, it could be 3 to 6 times that we are going to have inside of here, it's going to go and disturb the rest of our lines, right? We know that voltage drop is going to be based upon V is equal to I times R. And so anytime that I get a mass amount of current that's flowing through my lines upstream, right, the buses that these are all tapped off of, all of that current flows through there, which means we're going to go and drop voltage on everything else, which means that we end up seeing, you know, brownouts inside of our plants and stuff like that. In some cases, this is just annoying, you know, the lights dim for a couple seconds, but in other cases, it can be highly critical because if you brown out computer-based systems, the computer power supply is going to go and shut off. You know, you don't want to be shutting off computers and PLCs and controls and stuff like that just because you started up a large motor. It's not always feasible to go and increase the size of the system, the size of the service, or anything like that. So in a lot of cases, what we'll do is we will go to our alternate method, which is going to be known as reduced voltage starting. And it's not so much that it's always going to be a lower value of voltage that we are going to go and see. What it is going to be is it is going to go and reduce something so that ultimately we are going to go and have less current that is going to go and get applied to this. It's not always going to be the voltage, but in a lot of cases it will. We will class them as being reduced voltage, but just understand that it's the dropping of the voltage that we have to the motor itself that is going to go and allow us to drop the amount of current. Of those reduced voltage ones, we're going to have to place something in line. So basically what we had for a control diagram here, we would just modify this so that I have got some sort of methodology that is going to head of my motor, and it could be either ahead of the contactor or behind. Actually, I'll place it behind the contactor because that's where most of these are going to be. But there's going to be some sort of a control component inside of there that is going to be placed in line with the motor at the moment of startup. And then later on, once I get the motor up to running speed, then we would go and eliminate all of these so that it's just going to be a direct connection through. But it's that component in line with the motor that is going to go and give us all of that reduced voltage starting that we need. The 5 main types that we are going to go and deal with are going to be primary impedance, where we're going to go and place resistance of some sort in line with it. It could be resistance or reactance because we're using the term impedance. Auto transformer starters, where we're going to go and start them at a reduced actual value of voltage. Y delta starters, where we reconfigure our windings. We start them out as a Y, we then run them as a delta. You should be familiar with the amount of power and how that changes when we go from Y to delta. And then part winding starters, where we are going to go and only put in part of our windings. And last of all, solid state starters. We're going to go through all of them in varying depths, but we're going to explain what the fundamental theory is behind each one of these. Ultimately, all of these are going to go and have 2 steps as well. We are going to go and have a starting step. That's going to go and happen only during startup. And then that starting step is going to go and transition out once we go to running step. So if we were going to look at this thing, once again, as a timing type of diagram, what we would see is that at the moment that we apply power, As soon as we apply power, what we are going to go and have active is we are going to go and have our starting step. And then the starting step is going to go and operate for some time, and then either based upon the amount of current or time or something like that, the starting step is then going to transition over to our running step. And then we've got two main types of ways that this can go and happen. So my running step is going to be low until here. Now, I've got two types that I can have. I can either overlap the starting and the running, which would be what we would refer to as a closed transition, or I can go and have a break in between, which is what we would refer to as being an open transition. Over here, this would be an open transition type of start, where I'm going to go and apply power. When I apply power, it's going to go and give me my starting sequence, whatever that's going to be, and then when my starting sequence has partially accelerated that motor, there's going to come a point where I'm going to drop out and I'm not going to have anything to the motor. I don't have either the starting or the running controls going at that point. The motor is just going to be coasting at that point, and then I'm going to apply my running. What we will get out of that is we're going to go and get a little bit of line disturbance. Not as bad, but we're basically going to have nothing, and then we're going to go and hammer back on again. We get a little bit of a torque dip that the motor itself is not going to be provided with power. It's just coasting through, as well as we are going to go and have a little bit of mini inrush, but it's going to be much attenuated. The other type of transition that we can have is where we overlap these two, and it's going to result in a more complicated type of control, but this would be something that's then going to be referred to as being closed transition. Inside of a closed transition, what we see is that we apply power to the running position before we remove power from the starting position. It's just going to be a bit more complicated and has to be done safely. Sometimes it requires a few extra components. But if I don't want to go and see that, lots of power to the motor while I transition from one to the other, it's going to be my only option. Okay, let's talk about motor current and torque. We should be quite familiar with our types of design classes. We've gone through these in basic AC motor theory, and each one of these design classes is going to go and give us a different type of operation. Now, we saw this graph before, but when we saw this graph before, it looked like this, right? We saw this thing vertically, where we were looking at torque vertically, and then we were looking at slip going across from the left-hand side over to the right-hand side. It wasn't this exact same one, but if you go back into your AC motors, you should find that exact same type of graph. These are all going to go and give us a couple of things that we can go and run off of there. Speed, which is going to go and be based as a percent of our synchronous speed. We know that somewhere up in this range, most of our motors are going to go and be operating. Up in the mid to high 90s is what we're going to go and have for our speed, right? We're only going to have a small percent slip, which means that my 100% torque value, wherever that's going to be for each one of these, is going to go and define what that is going to go and be. So following this line up here, this 100% torque, we see that for the different types, for my design class D, I see that I've got a lot more slip off of it. It's operating at a smaller percent of my synchronous speed. If I go up then, I see that my design class C is a little bit better. And then if I go up again from there, I'm going to go and see that my design class A and B are basically going to go and be the same thing when it comes to actual operation. When I go to startup, at the instant of startup, I'm going to go and have 100% slip, which means that I'm then going to go and develop values of current and values of torque that are going to be based upon my construction of my motor, right? Because I don't have any rotation, I don't have any counter EMF, if I don't have any counter EMF, then I am going to go and have maximum amount of current that can go and flow inside of my rotor. And we know that ultimately the torque of the motor is going to be defined by torque is equal to K, the construction of the machine, phi, the flux that I'm going to go and have of my stator, which is always going to be constant. And then I'm going to go and have my I rotor and my cosine, or my power factor of that rotor itself. All of this is going to go and determine how much torque I have. And so ultimately what we're seeing is at the instant of startup, we are going to have a massive amount of rotor current in a lot of cases. And in some, we're going to have a really good large amount of current, as well as a very good power factor. The fact that we get a good power factor would be due to the amount of resistance that would be inside of the rotor, right? More resistance means that it's going to go and be, it's one of our ways we can correct power factors, add resistance in. So looking at these over here, design class D, It's going to have maximum current at startup like everything else. It's got a really good power factor. Therefore, it has got both of these working together, which gets us massive amounts of torque at what we see over here. Compared to a design A or B, design A or B don't have a high resistance rotor. So at the moment of startup, they're only going to be working off of the amount of rotor current over here. Design A, going through these, our original squirrel cage motor. This thing goes back until the 1800s. Normal starting torques, not great, 150% that we are going to go and have, and a relatively high amount of inrush current, just due to the construction that we are going to go and have. 6 to 10 times that we will go and get. They did improve upon that. They then went from the design A, they went over to our design B. And design B has got a higher reactance, so they worked at the XL formula that they had off of that one, which really meant that they were working off the L, the inductance in henries of the actual rotor. And then they managed to go and drop the amount of starting current to about 5 to 6 times. So it's almost halving the amount of inrush compared to the design A. We see that it doesn't maintain quite the same torque value. Over here I see that my dip on the design A is only coming down to about 125, whereas my dip on the design B is coming down to a little over top of that 100. But it doesn't make that much of a difference because ultimately both of them are going to get the same boost to go and begin this thing, that 150%. Design class C is just going to be a double rotor type of motor. It's got a high starting torque with a low starting current. The way that it's able to do that is we are able to go and have one rotor that's going to go and have a fairly high resistance, and we're going to have one that's going to go and have a fairly high reactance. And the high resistance one is going to have less induced into it later on, just due to the double squirrel cage design, because we're going to have currents from the other that basically counteract. It's an in-depth motor analysis to go through a double rotor, and take a look at lines of flux from the outside rotor that are blocking lines of flux to the inside rotor. Just, suffice to say that the more that we induce in the outside rotor winding, the less current that we're going to be able to go and push through to the inner one. And so it's going to go and drop away as we induce more into it. That allows us to create this design C type of rotor, which is going to have that high starting torque with a low starting type of current. They're a good type of motor. Most of the AC motors you are going to see are going to be either the design C or design B. The last one that we have is going to be my design D, which has got a high resistance type of rotor. Therefore, it's going to go and have a fairly good power factor. It's going to have wicked high starting torque, 250, 300% in that range. And it's going to go and have a low starting current because it has a high resistance in that rotor circuit. But it does also have higher slip that is going to be underneath load. When I take a look here up at load, I see that from 50 to 100, I see it's got a much greater range in speed compared to any of my other types. It is going to be better for heavy torque loads, but outside of that, it's not really something that we're going to play around a lot with. We will see design class D, high resistance rotors. We are going to see later on our wound rotor motors where we are going to go and adjust the amount of resistance that we place into the rotor circuit so we can go and spoof or simulate a design class D type of rotor, but we can actually take that out so we can, get a really good startup, and then later on we're going to be able to go and switch it down to like an A or B type. Okay, let's talk about voltage and current now on these actual motors. First of all, let's talk about changing a value of voltage to a motor. Ultimately, if I go and reduce my value of voltage to a motor, I'm going to go and reduce the amount of current that I'm going to go and have out of that motor. And this is just straight up Ohm's law. Let me just erase some of this over here. And let's go and take a look at Ohm's law. I is equal to E over top of R, V over top of R, whichever one you prefer to work with. Ultimately, we know that the resistance of a machine is going to be determined by the K, the construction. So it's not going to change anything. What we are going to go and have inside of there, we do just know that it is going to be a constant. So we can say that this is always going to be constant. So if I were to go and drop my value of voltage in half, I would therefore also have to drop my amount of output current out of here. And they give you an example of a motor inside of here where they say it's got a full load current of 10 amps. And when it started across the line, the inrush current is going to be 6 times. What's the inrush current going to go and be if I reduce it to 300 volts? And they're basically saying, look, if I had a 600 volt motor that had 10 amps of resistance, 10 amps of current, I can go and determine my value of resistance. We're going to work through a little different in the book. R is equal to E over top of I that I'm going to go and have. Let's just start by defining our value of resistance that we would have. So we'll say that 600 volt motor, 10 amps. Therefore, we are going to be able to go and say that my resistance would be 60 ohms, right? So 60 ohms is going to go and be that value of resistance. Then what we can do is we can go and say that since we know 60 ohms of resistance at running, and that's actually going to be a Z because it's going to be made of a resistance and reactance, I can say that, well, if that's what this thing is going to be, I can insert that into here because that's based upon my machine itself, 60 ohms. That's an extra 0 there, 60 ohms. I can go and place my value of voltage over top of there, 300 volts over there. And if I do 300 divided by 60, I should be able to go and drop the amount of current that I'm going to go and have. So if I do that, 300 divided by 60, that tells me that that thing would be running at 5 amps. And the question tells me that my inrush is going to be 6 times my running value. So if I was running it at 300, it would be running at 5 amps over here, which means that ultimately this times 6 would get me to 30 amps of inrush. So working through it this way or working through it in the book, you'll see the exact same thing. That's the startup on this motor would be 60 amps, and then that it would go and drop down to its 10 amp value. If I go and start it at 300 volts, then what I'd be able to do is I'd be able to start it at 30 amps, switch out my starting method, and then go to my full running, which would be at 10 amps. We'd see going to be a much, much smaller amount of overall inrush that we're going to go and see out of this thing. This does cause a little bit of a problem, though, because we know that our torque is going to be based upon our current. The torque is going to be based upon the current that is going to be inside of my rotor, as well as it's going to be based upon the amount of current that is going to be inside of my stator, because my stator is going to go and have ampere turns, which are going to go and create flux. So ultimately, if I'm dropping my value of voltage to the motor, I'm dropping the value of voltage to the stator, which is going to be dropping the amount of flux, as well as I'm dropping the amount of induced voltage that I would be able to go and get into my rotor, and therefore the amount of current. Ultimately, it just boils down to the fact that anytime that we are looking at torque and voltage, we say that torque approximately equal to, or directly related to, the square of my voltage. Torque is not the voltage squared. Don't take 240 volts and squared and say that's going to be your torque. It's just saying that the torque value is going to be directly related to the square of the voltage. When they're talking about the square of the voltage, they're not talking about the value of voltage, they're talking about this thing as a percent as well. So 100% would be a 1.0 that I would go and have, and 50% would be a 0.5 that we would go and use for that, and then we would just go and apply that to my selected motor that I'm going to go and have. We're going to do that off of this one over here. We're going to go and say that at 100% torque, my torque is directly related to the square of my voltage. So at 100% torque, that would be 1 squared, which is equal to 1. I would be getting, well, obviously all of my torque. So if I had design class D and I started up with 100%, I would go and have, we're just going to write this here as being full voltage. I would go and get this amount of torque to start out, between my 250 to 300%. If I had a design class B, I would be seeing this 150% at full value of voltage over there. If I were to drop my value of voltage down to 50%, 0.5, what I could then do is I could take 0.5 squared, which is going to go get me to a value of 0.25. And then I say that, well, I'm going to be getting 25% of my torque. So for those same motors, I'm going to go back onto this graph over here. 25% of this value over here, so let's call that thing 260, that this thing's operating at, somewhere around there. And this one here, 150. We would just go and take these values, 150 times 0.25, which would tell me that this motor itself would be starting out at 25%, so 37.5 would be where this thing would be starting at reduced voltage, 50% voltage. It would be a starting torque of that for my design B. Not very, very awesome. But if I take a look at this one over here that has 250 for its starting, 250 times 0.25 tells me that this thing would be starting up at 62.5 that I would go and have. So under that reduced voltage start, we would be starting somewhere about here. We see that my design class D is still going to go and have a higher value. Now you'll note that for both of these, what we have under reduced voltage starting is going to be less than the 100% that we have for that motor. And that's very important to go and note that when we start up under a reduced voltage, we cannot be starting up underneath full load. This means that if you're running some sort of a belting system, you would not be wanting to start up this motor with load already sitting on the belt. You want to start the belt empty and get the belts up to speed and then start loading stuff onto the belt. Or if you're driving a auger to extrude plastics or whatever it is that you're doing with this motor, you have to make sure that the motor is unloaded, because doing the reduced voltage does drop my amount of current, but it also drops that amount of torque so significantly. As always, this formula does have to go and be applied correctly. For us to go and correctly apply any of these, torques, we would have to know what the actual startup torque is. We never say that, if this is going to be at 50% voltage, that we're going to have 25% torque. No, we're going to have 25% of what the actual value itself was off of that. Okay, let's talk about the loads that we are going to go and have. Different types of loads are going to be coupled to our motors in different methods. We've got, some loads that are going to be basically direct drive with a pulley that we are going to use for things like, fans and stuff like that, where we don't have a lot of load. We're just starting to go and move air. Other times we're going to go and have, high torque applications that are going to be coupled together through the use of large, beefy gearboxes that are going to go and take whatever rotation we have from the motor and either speed it up, or in most cases, slow it down so that they can go and deliver more torque out of these things. When we do start up any type of a load, we have to go and select the proper type of voltage that is going to allow us to go and do so. In some cases, although it might be undesirable to see system disturbances and inrushes, what we get out of reduced voltage starting is just going to be too low. Those values that we saw before, the 37 to 62, were too low to go and start up that load. So you do have to go and factor in the type of load itself. If you can, we do want to go with the reduced voltage, because that is going to go and give us just less shock electrically to our system itself. However, if we can't start the load, it's just not going to go and work. That being said, if we also do the reduced voltage, we are going to have reduced amount of torque output, which can be a really good thing if I have got weak points inside of my cycle. It's going to minimize, the shock that I'm going to go and have, but it's going to go and cause me to accelerate for a longer time. And they do have a little important point across the bottom over there that any motor that will not start under full voltage, if I can't start it across the line, I'm not going to be able to go and start that thing using reduced voltage starting. It's just not going to work, because we're going to have obviously a smaller percentage of torque out of here. Okay, duty cycles are also going to have to be taken into consideration when selecting what I'm going to go and utilize. Duty cycle is just going to be how many times I'm going to go and run these things on and off. Every time that we start up a motor, we get a massive amount of inrush into that motor itself, which causes heat. Now, if that motor operates then for a while, it has a chance to cool down. It's still running, it's still going to have its regular amount of heat, but it's going to be able to cool down from that inrush. However, if I keep, jogging that motor, boof, 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 just kind of pushing this thing forward a button press at a time, I'm going to go and repeat that inrush tons and tons of times with no time in between to cool it off. So you got to go and watch your duty cycle, whether it can be used for, intermittent or continuous, etc. This is going to be out of your code book as well. We're going to go and talk about duty directly from the code. If you go to your code book, section 28 is going to be dealing with motors, and right at the very front of section 28, they give us some special terminology that we want to go over. First of all, non-continuous duty motor is a motor having characteristics or ratings described in section 0 definitions under duty as short-time duty, intermittent duty, periodic duty, and varying duty. So basically, anything that is any of these is going to go and be considered to be a non-continuous duty type of motor. A couple of other things we're going to go and have inside of here for definitions too. Locked rotor current rating. We've talked about this in class. They define it in the code book over here. It's basically going to be equal to 6 times the full load current if it is not marked from table 44 to table 45. This is what the code wants us to go and refer to. 6 times is going to be, if you look at our design classes over here, it would be a really good design class A, or it would be a relatively poor design class B that we would have. Let's go back to this duty over here, going to section 0, and then rolling down into duty. So over here. It's a requirement of service that demands a degree of regularity in the load. And we'll look at continuous duty last. Let's start by taking a look at intermittent. This is going to be a requirement of service that demands operation for definitely specified alternate intervals of load and no load, rest and rest, load, no load, and rest. So, this could be load that the motor's running the whole time, and then we take the load off of it, and then the motor's running, and then we take the motor continues running, we take the load off, we put the load on, we take the load off, we put the load on, like hydraulic pumps or something like that, where they just kind of run in the background, but we don't actually hear them load until we run them. Load and rest, where it's going to be loaded and then the motor shuts off. Or these ones here, where we're going to go and load, we're going to run a cool down period where the motor's just running with the fan pushing air over top of it, and then rest. But all of these are going to be definitely specified, which means they have to be done off of a timer, where the customer's not going to be able to go and change that. Periodic duty, it's a type of intermittent duty. So note that it says it is a type of intermittent duty. Once again, meaning that it has to be done through timers. If it's not timers, it's not intermittent, nor is it periodic. And this is in which the load conditions are regularly going to be recurrent. And then short time duty, requirement of service demands operation substantially constant load for a short and definitely specified time. This would be something like an elevator. It's going to be a short and definitely specified time. It's going to run up to this floor and then it's off again. It's going to run up to this floor and then off again. There's always going to be that time in between, because every elevator has got a timer on how long it takes for the door to go and open and the door to go and close, etc. And then this last one over here, which is just going to be varying duty. It's a requirement of service that demands operation at load and for intervals of time, both of which may be subject to wide variation. It's talking, once again, intervals of time. All of these over here, what I want to point out is in common to them is that they are timed. Different types of timing, but they are all timed. It's not just like, well, I feel like I'm going to run it like this today. If I don't know how somebody is going to be running that motor, if I'm like, today they could be running that thing for an 8-hour shift, and the next day they could be running it 24 hours, and the day after that they might run it only for 5 minutes, then I'm going to have to go with continuous duty, because continuous duty is indefinitely long time. Doesn't mean it's a long, long time. It just means that it's indefinitely long. It's indefinite in length. We don't know. So if your customer is not going to be running either the load or the type of service that they're going to go and have on the motor through a timer, if it's not through a timer, it does not class as any one of these, and therefore it has to be continuous duty, which means that 90% of the motors that you're going to put out there are going to go and be a continuous duty motor, because anything else, short time, intermittent, periodic, and varying, all deal with timers. If it's a time system, we can talk about non-continuous and apply rules, but most of the time we are going to be looking at having continuous duty types of systems. All right, going back into this one over here, talking about motor starters, if we know what the duty is going to go and be, we can also go and figure out what we need for our control components. If I'm going to go and have something that is going to be shedding part of my voltage at the beginning of startup, usually that's going to be resistance, reactance, or something like that, it is going to heat up during that operation, so I do need to go and allow it to cool down. If I know exactly how long it's going to be on for and how long it's going to be off for, I'm able to actually engineer a solution, which means undersize. That's all engineering ever means, is legally undersizing, because you're confident it's not going to go and fail. That's why engineers have to sign their drawings, is because they're saying, hey, this is the absolute minimum that I'm certain is not going to go and fail. And so anytime that we're looking at control elements, we can engineer them if we know what that duty is. If we don't know what that duty is, we have to go and treat them as being continuous duty, because you don't know if your customer is going to be jogging them, continuously heating up this starter, etc. Last consideration on startup is just going to be the power source requirements. Anytime that we have got a service that we are building, we have to fill out these design guidelines from BC Hydro, and BC Hydro, they'll send us power, but they want to know what's going to be there. They always want to know the largest horsepower motor on the job, because your motor could go brown out not just your location, but it could brown out a couple of neighbors as well. So they're going to go and ask us for either the maximum amount of horsepowers or the total amount of horsepower that we're going to go and have operating continuous at the same time. They'll ask you for your largest. They'll also say how many motors are you going to start up at the same time. And they want to know then, are we going to be across the line starting, or are we going to be reduced voltage starting? Usually that's going to be under a secondary or a follow-up that they're going to go and ask you for this. But on the initial one, they just want to know the maximum horsepower that you are going to have. And then if that, flags in their system as being, hey, that's maybe something we need to go and check into, then they'll ask you a bunch of these subsequent questions. But it's going to be very common that we have to be, ready to apply or to supply horsepower information to them. All right, read through the rest of this learning task. We've only gone through it in a half hour here. There's a lot of stuff that I kind of skimmed over top, but that's good information and in, selecting these starting types. We are going to start taking a look at the starting types, though, next.